Good day, everyone. This is Professor Friday coming at you one more time. We've had a request today for some trigonometric substitution. So we're going to take a look at the evaluation of the indefinite integral of x squared times the square root of 3 plus 2x minus x squared. Now, first step in any of these integration problems is figuring out what would be the appropriate technique of integration. Spoiler alert, I already said trig sub. But what about this problem indicates that we could have a trigonometric substitution be an appropriate technique for us? That's going to come from what's going on underneath this radical. Generally speaking, anytime you see a radical, trigonometric substitution is something that could take place. So what we're going to do is grab the quadratic that is underneath the radical, and what we're going to do is complete the square with it. Since it is quadratic in nature, that's what we're going to do. So what we'll do is we'll take the negative from the x squared and the plus 2x. We'll leave that plus 3 on the outside. For the purposes of completing the square, we grab that negative 2. Oh, hi, sweetheart. We take that negative 2, we have it, and square the result. By doing so, we get a positive 1. And that hi, sweetheart was for my cat Wednesday. She's going to make a cameo. How you doing, baby? Hey, sweetheart. All right. Well, she just knows when there's action going on in the basement, doesn't she? All right, so where were we? That's right, we were completing the square. So we had a plus 3 on the outside. So what we're going to do is take that 1 that we just got from completing the square. We will add 1 to this expression. However, in order to balance it out, we are going to need to essentially subtract 1 to balance it out. However, because the 1 that we added was on the inside of the parentheses and we had that negative in front, what we're actually going to be subtracting is a negative 1. Hi, baby. So with that in mind, we can take the 3 minus a negative 1. We can call that 4. And then we can also point out that we now have a completed square inside here, and that is 4 minus x minus 1 quantity squared. Now, with those things in mind, what we're going to do is rewrite the original integral in the following fashion. So that'll be still x squared. Then we'll refer to this as 4 minus x minus 1 quantity squared dx. Now, with all of that in mind, before we do a trig sub on this one, we're going to do a u sub. Trig sub is supposed to be used anytime we see a sum or a difference of two squares, especially when it is underneath a radical. So what we're going to do, hi sweetheart, is we will say let u be equal to x minus 1. And with that substitution in mind, we will also see that du is equal to dx, no problem there. But it also tells us that if we need it, we can also make the substitution that x is equal to u plus 1. Now, the reason I bring that up is because we're going to need it. Reason being, we need to make a substitution on this x squared as well. So x, we're going to replace that with u plus 1. So we'll call that u plus 1, quantity squared. And then also throw in a 4 minus u squared. Dx will simply become du because of our substitution over here. Now, with those things in mind, we see that this more readily takes on the form a perfect square minus a perfect square underneath the radical. So here's where we are going to make our trigonometric substitution. Now, when you see a number squared minus a variable squared, that indicates to me that we are going to make use of the sign. So we will let u be equal to 2 from the 2 squared times the sine of theta. Or equivalently, the sine of theta is equal to u over 2. What we'll also do is set up a little right triangle that indicates that. So theta is our angle, u over 2, according to some old hippie, caught another hippie tripping on acid, or as you might know it, SOHCAHTOA. That would give us u for the opposite, 2 for the hypotenuse, and Pythagorean theorem will get you that third side. And by an amazing coincidence, it happens to be the radical that we see in here. So, other things that we need to substitute. Du is going to be equal to 2 times the cosine of theta, d theta. And we can also observe from the right triangle that the cosine of theta is going to be equal to our square root of 4 minus u squared, that's our adjacent, over the hypotenuse, which is 2. So, with all of those things in mind, the substitution will become u, we just said was equal to 2 times sine of theta. So it'll be 2 times sine of theta plus 1, quantity squared, times our radical. If we solve this relationship for the radical, we will get 2 times the cosine of theta. du we already established as 2 times the cosine of theta times d theta. The next step that I'm going to do has absolutely nothing to do with calculus. The next step that I do will be all algebra all the time. Let's see if we can shift this down ever so slightly. Alright, so all algebra at this step. We will expand the 2 times the sine of theta plus 1. We'll get 4 times the sine squared of theta plus 4 times the sine of theta plus 1. That'll be multiplied by 4 times the cosine squared of theta d theta. Or since we have room for one more line here, let's go ahead and throw in that one more line. I'm going to distribute the 4 cosine squared theta through to all of these terms. We will get 16 sine squared theta cosine squared theta plus 16 times the sine of theta times the cosine squared of theta, and finally plus 4 times the cosine squared of theta. That will all be d theta. So what we wind up with inside of our radical are 3 very similar looking integrands, or 3 very similar looking terms that get integrated in wildly different ways. So what I'm going to do is go ahead and label these as 1, 2, and 3, and evaluate them all separately. So, with that in mind, heading back up to the top of the page, I'm going to start a new page, but I'm going to include these 3 integrals in our calculation. So, integral number 1 from the previous page was 16 times the sine squared of theta times the cosine squared of theta d theta. Now, powers of sine and cosine tend to be really easy as long as one of them is odd. If one of them is not odd, then we get to use the power reducing identities. Power reducing. So the 2 power reducing identities that we're going to make use of are going to be that the sine squared of theta is equal to half of 1 minus the cosine of 2 theta. And the cosine squared of theta is the same identity, but with a plus sign instead of a minus sign in between them. Both of these come from the double angle identity for the cosine. So what we're going to do is apply both of these. We'll have 16 times sine squared of theta will become half of 1 minus the cosine of 2 theta. And the cosine squared will become half of 1 plus the cosine of 2 theta. Make sure that we know that there's a little separation between those. So what I'm going to do is take the 16 and the 1/2 and the 1/2. I'm going to multiply all of those together. We will get 4. Then I'm going to take 1 minus the cosine of 2 theta and 1 plus the cosine of 2 theta. And as I frequently say at parties, the product of binomial conjugates is a difference of perfect squares. I don't go to a lot of parties. That's okay, though. So we get 1 minus the cosine squared of 2 theta. The approach for this can be a little bit different. What I'm going to do is recognize that 1 minus the cosine squared is actually a Pythagorean identity. And I'm going to change that over into sine squared of 2 theta. Which leaves us with the same situation that we were just talking about. What do we do if all of our powers of sine and cosine happen to be even? Well, we're going to use power reducing one more time. So that'll be half of 1 minus 4 times the double angle. However, our double angle has grown. Our original angle was now 2 theta. Our double angle is now 4 theta. I can take the 4 and the 1/2, combine those together as 2, and I am ready to integrate the rest. Integral of 1 is going to be theta, and integral of the cosine of 4 theta is going to be the sine of 4 theta all over 4. Now normally we would tag on a plus c, but we also recognize that we got a couple more integrals that still need to be done. So instead we'll just call this 2 times theta minus half of the sine of 4 theta. That sounds like it's going to be fun on a bun. All right. One integral down, a couple more to go. Integral number 2 from the first page. Taking a look at it right now, this was the integral of 16 times the sine of theta times the cosine squared of theta, d theta. Good news on this one is that we have exactly the scenario that we like to have in this situation, which is at least one odd power of the sine or the cosine. Now what we're going to do is perform a u substitution. We will let u be equal to the cosine of theta, and therefore du will be equal to the negative sine of theta d theta, meaning that we can take the sine of theta that we had and the d theta, those two things together will become negative du. Everything is accounted for except for the negative sign. So putting these things together, we will get still 16. Cosine squared will become u squared, and then the other part becomes negative du. The negative and the du are, the negative and the 16 are both constants. We can pull those out and then integrate the u squared with respect to u. Of course, substituting back gets us to negative 16/3 times the cosine cubed of theta. Again, normally we would also see a plus c associated with this, but we're not nearly done with this problem. So let's keep it going. For the third integral was the integral of 4 times the cosine squared of theta d theta. Great news here is that we already know what to do with the cosine squared. We did something very similar to it in integral number 1. We'll take half of 1 plus the cosine of 2 theta. That's our power reducing identity one more time. The 4 and the 1/2 can be combined together into a 2. Everything else is ready to be integrated with respect to theta. That gets us here. That'll be 2 times theta plus the sine of 2 theta all over 2. And we can go ahead and distribute that 2 through for funsies. That'll be 2 theta plus the sine of 2 theta. Now is the point where we can tag on that plus c, just to give us a quick reminder as to where everything came from. If I pulled that away too quickly, please feel free to rewind and bring it back. So as a reminder is where everything came from. This was 1 plus 2 plus 3. What I'm going to do is, from my side paper over here, copy down what the results were. So the result of integral number 1 is we got 2 theta minus 1/2 times the sine of 4 theta. From integral number 2, I got minus 16/3 cosine cubed of theta. And then from our integral number 3, I got plus 2 theta plus the sine of 2 theta. All of that we can tag on a plus c. So here was 1, and 2, and 3. However, we are not by any means done with this problem, because now we need to start the arduous task of actually substituting back. Now, with those things in mind, I think that we're going to need to make use of a couple of identities here. Actually, some algebra would probably help first. Let's combine any like terms that we see. It looks like we got a 4 times theta, and we'll do minus 16/3 times the cosine cubed of theta. We got minus 1/2 sine of 4 theta, and then plus the sine of 2 theta. Looks good so far. Now, these substitutions came from, I'm going to scroll up just a little bit here. These substitutions started right back here as far as the theta was concerned. So anywhere I see a sine of theta, I'm going to put a u over 2. Anywhere I see a cosine of theta, I'm going to replace it with radical 4 minus u squared all over 2. Now the problem that we're going to run into is we have a couple of double and quadruple angles in our expression here. So with that in mind, we're going to make use of a couple of additional identities. First identity that we're going to use is the double angle identity for the sine. That is, the sine of double an angle will be 2 times sine of the angle times cosine of the angle. However, given that we have 4 theta here, that is double 2 theta. So when we apply the double angle identity, we're actually going to need to apply it again. I suppose I can do the same for this guy over here and call this 2 times the sine of theta times the cosine of theta for the sine of 2 theta. Let's do a quick step of algebra rather than trying to continue to substitute back. We'll call this 4 times theta minus 16/3 cosine cubed theta. The 1/2 and the 2 will cancel each other out, so this will still be minus sine of 2 theta times the cosine of 2 theta plus 2 times the sine of theta times the cosine of theta. We will now proceed to do another double angle identity on the sine of 2 theta and the cosine of 2 theta. So 4 theta minus 16/3 cosine cubed theta minus, for the sine of the double angle, 2 times sine of theta times cosine of theta. For the cosine of 2 theta, we do have options. I think the double angle identity I'm going to use for this one is going to be 1 minus 2 times the sine squared of theta. Of all the substitutions, I think sine is going to happen most easily, so we'll go with that. Once in this form, we are ready to substitute back. So, once again, this came from sine of theta is equal to u over 2. Solving this for theta, we'll get the arc sine of u over 2. So 4 times the arc sine of u over 2 minus 16/3 times cosine of theta was equal to the square root of 4 minus u squared over 2 raised to the 3rd power minus 2 times the sine of theta times the cosine of theta times 1 minus 2 times sine squared of theta plus 2 times the sine of theta times the cosine of theta. Holy crap, do we have algebra to do. Yeah, there's a lot of algebra that can take place. But just as important as the algebra is the fact that we still have one more substitution to go. The original problem didn't ask about u, it asked about x. So we need to substitute back. We need to replace all of our u's with x minus 1's. So replacing the u's with x minus 1's, we will get this nice arduous looking task. U becomes x minus 1 minus, let's see, cube the 2, that'll be 8. 16 and 8 can reduce down to 2/3. Then we'll call this the 3/2 power. Let's see, what did we just say? X minus 1 squared, and then 3/2 power. Minus, oh boy, minus, we can cancel a 2 with a 2 and get a u times 4 minus x minus 1 quantity squared to the 1/2 all over 2. You know what, there's not enough room on this line. Let's try this again. Let's start a little lower this time. 4 times the arc sine x minus 1 over 2 minus 2/3 times 4 minus x minus 1 quantity squared to the 3/2 power. Minus 2 and the 2 will cancel out to give us a u, which is x minus 1. And then square root of 4 minus u, which is x minus 1 squared, all over 2, times 1 minus, square in the 2 will give us 4. 2 and the 4 reduces down to 2. We'll go to u squared over 2. Plus 2 and 2 cancel out. Shoot, we just said that that should be x minus 1 quantity squared. Gross. 2 and the 2 cancel. We go to u times square root 4 minus u squared all over 2. And of course, don't forget about your plus c's. If you want to do more algebra after that, I hope you have a lot of spare time. Anyway, hope you enjoyed. Hope it was helpful. Hope you have a wonderful night.